it is that time of the semester for the second semester of physics to look at electric potential. So far we've looked at the electric field due to point charge, electric field due to dipole, electric field due to charge distributions. We've looked at the difference between conductors and insulators. And now we have this electric potential thing. So here's what I'm going to do. This is what I'm covering today. There's a lot of stuff here. I have no idea how long it's going to take. Number one, we're going to review work energy. So I'm going to do a work energy problem, something simple. And then I'm going to do work energy for a charge in a constant electric field. After that, I'm going to show you that actually the path doesn't matter when you're calculating the work in a constant electric field, and it turns out for any electric field. Then I will define the change in potential energy, the electric potential energy for that constant electric field. Then I will define the electric potential, not to be confused with potential energy. And then we will calculate the electric field for a point charge, a change in potential for a point charge. And finally, I will go over the relationship between the electric field and the change in potential. Let's get started with an example. Okay, so you may have forgotten the work energy principle, and that's cool. Okay, well, it's not cool, but. So we define work for a constant force as F dot delta R. So if you remember, if I have F as the vector Fx, Fy, Fz, and delta R as a displacement, I'll call that delta x, delta y, delta z. Then the dot product of F and delta R, what I do is I take the x components, multiply them together, plus the y components, multiply together, plus the z components, multiply together. So in general, this would be Fx delta x plus Fy delta y plus Fz delta z. And now any of these could be positive or negative. I can move in the positive or negative direction, and the components could be positive or negative. So the work can be equal to 0, the work can be equal to a positive number, or the work can be equal to a negative number. All those are possible. And we use the units of joules for work. If force is measured in newtons and displacement is measured in meters. So 1 joule is equal to 1 newton meter. Okay, so let's do and then what about energy? Well, energy depends on our system. So let's just think about the system of a ball falling. So here's a ball of mass m. It starts with the velocity v1 equals 0. One of the other important things is that work and energy are scalars, so I actually don't really care about the direction right here. One of the fundamental types of energy that we have is kinetic energy. So kinetic energy is 1/2 mv squared. So let's say I let this ball fall down here it starts at a height of y1 and ends up here at y2 equals 0. It hits the ground. And so I want to find the velocity v2 at the end. So if I take the system of just the ball, then there's no such thing as a potential energy if you have one object. And I can calculate the work done by the gravitational force, mg. So I have my displacement delta r is going to be 0 in the x direction. And the final y is going to be 0. So this is going to be negative y1 is the displacement in the y direction, and then 0. So mg and then g is 0, negative 9.80 newtons per kilogram. So mg dot delta r is going to be equal to, the only thing that's going to survive is this, right? The 0 times 0 and 0 times 0 just go away. So I get a negative times a negative, so I get plus m, I'll choose the magnitude of that g, y1. And that's going to be equal to the change in kinetic energy, so it's going to be k2 minus k1, but k1 is 0, so it's going to be 1/2 m v2 squared, and I can use that to solve for v2. So v2 equals, the mass cancels, and I multiply by 2 and take the square root. The square root of 2gy1. So that was a simple work energy problem. But it turns out that since the work done by the gravitational force does not depend on path, I can actually move that to the other side of the equation. So I can say work equals 0 equals delta K minus or plus delta U, where delta U is equal to negative mg dot delta R. It's the negative of the work done by gravity. And it's negative because I moved it to the other side of the equation. Okay, so that's how we get this idea of change in potential. The change in potential is the negative of the work done by the force, and you can do that only if it's path independent. So that's your work energy review. Let's do this for a particle in a constant electric field, and I'll show you how it doesn't depend on the path. So let's say that we have a charge plate. This is positive. And then a negative plate. And if I have these two parallel plates with uniform charge, then I have constant electric field. And we don't even care. I'm just going to say E equals some value. I'm going to pick this as, let's say, 10, 0, 0 newtons per coulomb. I just picked that. And let's say I want to find the work done by the electric force by moving a charge plus Q a distance across here of S. So it's going to go over here. And it released it from rest. So I can do the exact same thing. This is the exact same problem as the gravitational problem we just did, except it's turned sideways. I can calculate the force. The electric force is just going to be, this is Q, QE. And then delta R is going to be S. It's going to be, if we call this, it doesn't really matter what this is. It doesn't matter what the X value of this is. It definitely moved over a distance S. So this is going to be S, 0, 0. So now the work done by the electric field is going to be F dot delta R. And that's going to, not even going to use that number. So I get QE in the X, this has an X component, right? So it's only in the X direction. I can write this as the magnitude of E times 1, 0, 0. So the E, 0, 0. So it's going to be QE is the force, and the displacement's S plus 0 plus 0. So the work is going to be QES. And that's going to be equal to the change in kinetic energy. And we could find the kinetic energy, we could find the speed. You would need the mass of the particle. The masses don't cancel in this case because here the electric force depends on the charge, not the mass, like gravity does. But you could find the mass and do all this stuff. I just don't want to do it. Okay. But the thing is that I could move, if it doesn't depend on the path, I can move that to the other side. So let's see. If I go here, I'm going to take a new path. I'm going to go down. Let's call that, what should I call that value? D. I'm going to go down D, and then I'm going to go over S, and then I'm going to go back up D. So let's find the work on this second path and see if we get the same thing. If we do, then that suggests we can use this as a potential and move to the other side. So I'm going to say the work is going to be F dot delta R1 plus F dot delta R2 plus F dot delta R3. So this is going to be 1, 2, 3. So I have 3 paths. So delta R1 is going to be equal to 0, negative D, 0, right? Because I'm not moving in the X direction, only moving in the Y direction, a distance down of negative D. So that's my delta R1. Delta R2 is going to be equal to, I'm now going from here to there, so I'm moving over a distance S, so 0, S, 0. And then delta R3 is going to be 0, positive D, 0. I'm going up. So if I do this work, I know my expression for my force. Let's write that as F equals QE 0, 0, because it's only in the X direction. So if I take this first dot product, F dot delta R1, it's going to be QE times 0, which is 0, plus 0 times negative D, which is 0, times 0 times 0, so 0. This one for 2, I'm going to have this is S00, sorry. So I get QE times S, so I get plus QES, and then 0 times 0 plus 0 times 0, and then finally I get QE times 0 plus 0 times D plus 0 times D, so I get 0. So it's QES. So that's the exact same work as done before. It does not depend on the path. You can pick all sorts of paths. I could pick a path like this, which would be more fun, but I didn't want to do that at the point. And I get the same thing. Okay, so since that's true, I can take the work done by the electric force, move it to the other side, and define that as the change in electric potential energy. So delta U, I'll put a C for Coulomb potential, is equal to, for a constant electric field, negative Q E dot delta R. This is just the force, and that's the displacement. And then there's a negative sign because that's the negative of the work done. Okay, that is the electric potential energy. Technically a change. It's always going to be a change because work is over a displacement. So we're really talking about the change in electric potential energy. So I should put that. Change in electric potential energy. Now, what if I take that change in potential energy and divide by the charge? And this is just still for a constant electric field. So let's say delta U equals negative QE dot delta R. That's what we said. And this is only for a constant electric field. Constant E. We'll do non-constant E in just a second. And I divide both sides by charge. Then I get delta U over Q equals negative E dot, that's a vector, dot delta R. And we define this as delta V. So it's the charge, the potential energy per unit charge. So delta V is the change in electric potential. It's the potential energy per charge. And it has units of joules per coulomb, which is equal to a volt. So a lot of people call this change in potential, electric potential, voltage. And I guess that's fine. It'd be like calling distance meterage or current amperage, which people do. No one calls distance meterage, though, do they? I don't think so. So if you call it voltage, I'm not going to get upset. Well, I call it voltage every once in a while, but it is the change in electric potential. And so if E is constant, then delta V equals negative E dot delta R. And if you're moving in the same direction, this would be negative ES, right? Because that's what we had before. Okay, so I'm checking back my list. I want to do it in the order because I kind of thought delta. Okay, let's do delta V for a point charge because a point charge does not have a constant electric field, and that would be more fun. So remember that we use that constant electric field a lot, but that result is only for a constant electric field. Let's suppose I have a point charge at the origin, Q, and I know the electric field. It would be this. It's any location, R. E would be 1 over 4 pi epsilon naught. Q, that's not a vector. E equals 1 over 4 pi epsilon naught. Q over the magnitude of R squared times R hat, where R hat is a unit vector in the direction of E. Now, what if I want to find the work done by this? How do you find the work done by a non-constant force? In general, work is the integral from point 1 to point 2 of F dot dr. Right? This assumes that the force can change, and so what we're doing is breaking this into tiny, tiny, tiny little pieces over which the force would be constant and doing the dot product and then adding up all those little pieces. Now, this is a path integral, so it actually could change direction too and make it much more complicated, but let's just assume that we're in the same direction. So we're going to start from right here, some distance r initial, and then we're going to go to r final. So if I want to say this for the electric field, this is the force on some charge, I'll call it QT for the test charge, and that's Q, is going to be equal to, from R initial to R final, of Q test times E dr. And that's the work done. Now the change in electric potential energy is going to be the negative of that, negative Ri to R final Qt, that's the test charge, E dr. And E and dr in the same direction, so I didn't have to worry about, I can turn that into a scalar component. And then if I divide both sides by that test charge, I get delta V equals negative the integral from Ri to R final E dr. And I can use this as my magnitude of the electric field and integrate. So let's do that. So delta V is negative the integral from R initial to R final, 1 over 4 pi epsilon naught Q, and this is the charge at the origin, over R squared dr. Okay, so I've already taken into account that dr and E are in the same, both in the same direction. They could be the x direction, it doesn't really matter. And I have a pretty straightforward integral because my integration variable is dr and my variable is r, so I can do that. So let's write this as negative 1 over 4 pi epsilon naught Q times the integral from Ri to R final of r to the negative 2 dr. And I wrote it like that as a power rule so we can remember how to do integrations that way. So if I integrate this, I can just add 1 to the power and then divide by that, so it'd be divided by negative 1. So I get negative 1 over 4 pi epsilon naught Q, and then I have 1 over r, negative 1 over r, from R initial to R final. And I do mess up the sign quite a bit, so if I mess up the sign, I'm going to go ahead and ask for forgiveness, delta V. And then I can say delta V equals negative 1 over 4 pi epsilon naught Q times this negative 1 over R final minus plus 1 over R initial. Okay, so now let's consider the case where the initial potential is, this is true, but assume that V at R equals infinity is equal to 0. So I'm actually going to set that true. So now if I start with Ri equals to infinity, so I start an infinite distance away and move to the location Rf, then this is going to be 1 over infinity, which is 0. I know math people don't like that if I say that, but come on. Let's be realistic here. So that means I can write V, and this is going to put with respect to infinity is equal to 1 over 4 pi epsilon naught Q over R. And that's well, you'll see this a lot. We use it a lot because it's actually quite useful. This is the electric potential with respect, due to a point charge, with respect to infinity. Okay, I'm going to add something in here because I think it's important. And then I'll show you that last thing. And the thing is, what if I have this? Suppose I have a dipole. So these are negative Q and plus Q separated by some distance S. And I want to find the electric field at some location, let's say right here. Well, that would be E plus, the electric field due to the positive, and that's not really drawn right, E minus due to the negative charge, and I can add that together. So E equals E plus E minus. We call this the superposition principle. It turns out that this also works for electric potential if I have the electric potential with respect to infinity. So suppose I want to find V at that location. V at some function at location R is going to be V plus V minus. So if I just need to find this potential with that R, this potential with that R. Now there is something extremely different here with electric fields. This is a vector addition, and this is not. This is scalar. So it's actually easier. I don't need to deal with the directions. I just need that value, add the two values together with respect to infinity, and this will be the potential with respect to infinity. Okay, let's see. So what else did I have on here? Oh, so what's about the relationship between E and R? So remember, delta V equals negative the integral from R initial to R final E dot dr. That's true. Okay, and we did that for a point charge, but any electric field that you have, any expression of electric field, even for a dipole, I could get the potential two ways. I could do it by finding the potential due to each point charge, or I could use the electric field due to a dipole and integrate. Okay, and so I'll probably show that at some point. It's fairly useful. Don't forget that negative sign. And that negative sign is because this came from the work done by the electric field, and we moved it to the other side of the equation. Now, what if I want to go backwards? What if I want to take an electric potential and find the electric field? This is how I find the potential from the field. What if I want to go backwards? Well, there's two problems here. One, this is an integral, so I need to undo the integral. How do you undo an integral? And that's with the derivative. And two, how do you undo this dot product? Because this electric field is a vector, and that's a scalar. So how do you take a scalar and get a vector? And the answer is this. I'll just write it out. So let's say let's say I have some function of potential as a function of x, y, and z, then E is going to be the vector negative the partial of v with respect to x for the x component, negative the partial of v with respect to y, negative the partial of v with respect to z. So this is actually called the gradient. I can take the gradient of all these. I have to see how it changes in the x direction, how it changes in the y, and how it changes in the z. So we actually write this as E equals negative, I would call this the del operator, v. Some people call that nabla. I don't really know why. I never called it that. So that is your connection between, if I want to find the potential, I need to integrate. If I want to find the electric field, I need to take the derivative 3 times. And there's still that negative sign there because of the work thing. So, okay, that is your super quick introduction. That was pretty quick, right? 22 minutes, 23 minutes. Introduction to electric potential. We're going to do some problems with this. It's going to be great fun. Do things like that. I want to show you the electric potential due to a point charge, but do it numerically by breaking it into a finite number of pieces and comparing it to the electric potential due to a point charge. But there you go.